Hey, Topic Life Math and History, and we're gonna take a look at systems of inequalities. So recently, we have been taking a lot of looks on having the linear lines as inequalities on a graph. And the only difference is even though that they're in slope-intercept form, their operator is not an equal sign. They're totally different. So in the last video, we have been taking a lot of looks on what makes the inequalities linear and what they look like on a graph. But if you ever watch our previous video, systems of equations instead of systems of inequalities, in that video, we were talking about how, on the graph, the two lines are intersecting each other, and the point where they intersect would make the two equations true. Like, if you had an intersection of these two lines, that is systems of equations. But can you guys guess what systems of inequalities is? Systems of inequalities are gonna have lines that intersect. But instead, just like the previous video, we are going to have beautiful shaded in areas in the graph. So there's going to be more answers than you expect. Because here's an example. If we try to graph y is greater than or equal to 2 over 3x plus 3 and y is greater than negative 4x, 4 over 3x minus 3, if we place them on a graph, we should be expecting to have the graph have beautiful shaded colors and have a mostly shaded area. When you have an area that is shaded and it also becomes true for both of the equations, that tells you that whatever in those shaded areas or the point in that shaded area makes the equation true that represent the values for x and y. Let's graph the first equation, the blue one. Y is greater than or equal to 2 over 3x plus 3. So the first thing is to modify the equation and turn it into something else. What we have to turn it into is, think of it as y equals 2 over 3 x plus 3. Okay, now we get rid of this equation and replace it with this sign right here, greater than or equal to. Okay, we now have the blue equation on the graph. Now, all we need to do is do the green one. Y is greater than negative 4 over 3x minus 3. But we can interpret that as y is going to equal negative 4 over 3x minus that by 3. Let's put it on the graph. Okay, now we can get rid of this equation and replace it with the greater than sign. Y is greater than negative 4 over 3x minus that by 3. Great! Now we have put the green equation in. And what's weird is this is what the graph looks like when you saw it in the clip. So, with the two inequalities, instead of having equations where the two intersect that have one line that makes the equations true, we have an area that makes the equations true, because this area right here, this area is actually the area that's going to make the blue and the green equation true. That's because they're both connecting each other, or they're both in that same area. If you were to find a point in the blue area, then it would make the blue equation true, but the reason why it would not make the green equation true is because it's not in that area. Even if you do it mathematically, whenever you put in for x and y, putting in that purple dot or that point on the graph will make the blue equation true, but the green equation false. Vice versa with if I put the purple one on the green one, and if that purple and blue never existed, then it will make green true, but blue not true. If I put the purple dot in the middle of where blue and green intersect, that will make both equations true. If you do it mathematically, it will make both equations true. So when you look at a picture of a beautiful art like this, there are going to be 4 different areas that you will see on the graph. With the non-shaded area, that means there's no association here. So no association. If you find a point on the graph that has a dot here or here that only associates with one equation because they're in those areas, we're going to say that there's 1 and 1 because it satisfies only one equation, this one or that one. If we put a point or an answer right here and insert it into our math formulas, then we're going to write 2, because whatever dots you put in here will satisfy 2 of the equations. Let's find 2 points, one that makes 2 of the equations work, and one where only one of the equations work. Let's see on the graph. Okay, here are the 2 points. We have -2, 2 as in x and y. And we also have -6, 1 as in x and y. But since they're points, we must put them in parentheses. Will they fit for the 2 equations? So we'll have to insert them into the 2 equations for x and y and see if they make sense. Let's start with this equation first, and we'll insert them into these 2 equations. So let's do the math. So we're going to put in -2 in for x, and we're going to put in 2 in for y. Does this satisfy the equation when we insert those numbers in for x and y? Let's see what happens. So we're going to turn this into a fraction of -2 over 1. Then what we're going to do is have an answer, multiply these 2 together. You'll get an answer of -4 over 3. Then you have to add that by 3 because you have that 3 left. And when you do that, you get an answer as 1.66666 repeating. And we have 2 for y. So will this fit into the equation? Is 2 greater than or equal to 1.666 repeating? If yes, then this works. Check! What about the other one? So we have y is greater than -4 over 3x minus 3. Insert -2 in for here, and then insert 2 in for here. So that multiplied by that, negative times a negative is a positive. And we're going to put this as -2 over 1. So we get +8 over 3. And when we do that, we're gonna minus that by 3, and 8 over 3 minus that by 3, that is negative 0.33333 repeating. And we have y for 2. So it's 2 greater than negative 0.3333. If yes, that also works. So the point negative 2, 2 can be a satisfied input and output for these two equations. Here is where the point is. So yes, it works because the point is in the two lines right here. Let's do the equation that only satisfies one equation. So it's negative 6 comma 1. We have y is greater than or equal to 2 over 3x plus 3, negative 6, 1. So doing that, we're going to get 12 over 3, which will become 4, or negative 4, because it's a negative 6 being multiplied, plus 3, that is going to be negative 1. So, is 1 greater than or equal to negative 1? Well, 1 is greater than or equal to negative 1. So this makes it true. But what about the next one? We have y is going to be greater than negative 4 over 3x minus that by 3. Put in negative 6 and 1. And when we do that, we're going to get 24 over 3, because this 1 is going to be here. But it's going to be a positive, because a negative by a negative is a positive, which will become 8. And we also have minus that by 3, so 8 minus 3 is 5. But hold on. If y is 1, y equals, y is greater than 5, I don't think 1 is more than 5. So this doesn't work. This statement does not work, which means that negative 6 comma 1 satisfies only one equation, the blue one, not the green one. So that is how you mathematically prove if a point works for only one of the equations, none of the equations, and both of the equations. That is how you basically find another way of, instead of having two lines intersect, but we now have two areas that intersect. That is how we can understand systems of inequalities. I hope this video has helped you. Thank you for watching Taoping Airlines Math Industry. Like and subscribe.